Alright, hello, welcome. Sorry. So today, we'll start with Abhishek. So I just wanted to say one thing is that the session after this is kept as a sort of a free interaction session, right? So we were talking with speakers, and what we figured out we'll do is that maybe we'll just go around and have a round of introductions of all the participants, like where are you from, and what sort of problems do you work on. I think that'll be nice. And then the three speakers, so Abhishek, Arnav, and Edgar are going to be around. You can just catch them and discuss with them whatever questions or additional things that you have to discuss. So they'll be available till lunchtime to discuss. So that's the plan for the first interaction session. And then the second interaction session, also we have a tentative plan, which I'll announce at lunch once it is finalized. Abhishek is looking at me. Okay, so Abhishek.
Okay, so today the original plan was of my lectures was this. So right now I thought it's better to just get across this 1 and 2 clearly, and the 3 and 4 are more. In some sense, there is no calculation. Sorry, go. Okay, so 3 and 4 are sort of more, general discussions and sort of, there are no calculations and so on. Okay, so I will go into that, but, I'll spend very little time on 3 and 4. So today let me start again by just summarizing what all so far we have learned, and there were some few points which I thought I would clarify because there were many questions. Okay, so this is what the general idea of stochastic thermodynamics was. So we have stochastic. So we are looking at Markov processes first of all always, and we looked at two kinds of processes: continuous processes described by Langevin equation. So continuous in time, they are involving continuous, and then what we call jump processes. Right? So both of these are Markov processes, but one involves continuous change and other involves jumps. And then for these two processes, we discussed that you can write something equivalent to the first law. And in a given trajectory, you can ask what is the change in energy, what is the work done in this particular step, and what is the amount of heat absorbed or given to the reservoirs. Okay, and then so first we discussed the first law, and then we tried to discuss some analog of the second law. And for this, what we needed is to generally, if you think of second law, we discuss entropy. Right? Entropy is usually defined in equilibrium, and there it's related to if you're in a given thermodynamic state, you can define entropy, and of course you can, even without StatMech, there's a definition of entropy. But then from StatMech, we know it's given by you need an ensemble picture. Right? So a given system is described by either microcanonical or canonical ensemble, and then in the microcanonical, it's the most basic ensemble. And there, the idea is you count the number of states at a given energy, and that gives the entropy. Okay, so it's not associated with one state; it's associated with an ensemble. Okay, and but in stochastic thermodynamics, we want to say what is the entropy produced in a given path. Right? So that's quite a different concept. And here, to introduce this idea of entropy produced in a given non-equilibrium process, one introduces this notion of trajectories. Right? So basically the idea is given a stochastic process, I can ask what is the probability of a particular trajectory in time. So whatever my configuration, I looked at single variables, but it's flashing here.
Oh, I just see. Also, this is for
Yes, so but can people hear it back? No.
We can hear the line because I have taken lectures in this point.
Okay, so I just say speak loudly. Okay, so basically we looked at, so there's a system is described by some set of variables x, and I discussed mostly like single degrees of freedom, but this can be any number of variables, and then we look at time, and we have some stochastic trajectory, which at time, the starting time is at x naught, and the final time is at x in something of xt, and this path is described by x of tau. So tau goes from 0 to 3. And in this, so I can discuss both. If I am thinking of non-equilibrium processes, then typically there's some parameter in my dynamics which can change with time. So, so this is one way I can introduce a non-equilibrium process by changing some parameters as a function of time. Then I also discussed that we can describe, generate a non-equilibrium process by including non-conservative forces. One other way to generate non-equilibrium states that I didn't discuss is like by introducing some boundary drive. Okay, so you need not have any non-conservative force, but you don't have any time-dependent force. But for example, if you take a chain of particles and you connect them with at different temperatures, right? Not at one temperature, but it's at two temperatures. So this also is a system which you can describe by the same set of equations, and you can use almost the same formalism. But here there's the driving is because of differences in boundaries. Okay, so these are boundary-driven non-equilibrium states. You can generate non-equilibrium states.
So important that these are harmonic chains, right?
No, it's you can do anything.
Even anharmonic.
Dynamic chains, you can put electrons interacting with one, you can put different chemical potentials. So you can generate these non-equilibrium states in various ways. You can put any kind of system here. And one interesting set of systems is like really small, like you can put a benzene molecule where fluctuations are really important. Right? And you can ask, connect a battery across this. What is the current in the system? What are the fluctuations? I mean, can you have like current going in the wrong way? That's like negative entropy produced, right? So you can ask all these sort of questions. So this is something I didn't discuss, but it all falls within the same formalism. Okay. So now what we discussed is that, okay, so this was, first I discussed this probability of forward by reverse path conditioned on you start at x0 or you start at the end point. Right? The reverse path starts at the end point. So that's the conditioned thing. So this is conditioned on you started on x0, and then this is just given by the exponential of the entropy generated in terms of just heat absorbed by the bath. Okay. And then I said that you can also choose this initial condition x0 or xn from some distributions which let's say called p0 and pn. And then in that case you would ask what is the joint distribution of x0, x1 to xn. So this would be multiplied by what is the probability that x0 is chosen by from some distribution. So then if you give this ratio, you just obviously get this, right? And then this I defined as, this whole quantity is defined as, that's taken as the definition of entropy produced in over a single trajectory. Okay, now discuss various consequences of this and this definition and then this result. So one is, yeah.
These systems that where you set the gradients, like temperature and all.
Right, yeah.
How do you define what like there is no time?
Okay, yeah. So here maybe as Of course, you can introduce also time dependent. In addition, you can introduce time dependent. So that would still give work. Otherwise, it will just have heat. And there's no, yeah, so it's just heat is, there's no work done yet. Okay, so, yeah, so in this system, obviously change in energy is just heat absorbed from this bar plus heat absorbed from this bar. So you can just call it Q left plus Q right. That's just the first law. And but it immediately follow from the equations. Okay, and this will be fluctuating. Okay, so now the other important thing that I wanted to emphasize is that in this definition there is a freedom to choose these distributions at the endpoints. Right? So I mostly discussed. So there are various choices of. Okay, so if you choose this, let's say P of n in general, x is equal to. Okay, so you will have some time dependent parameters, but if you fix the parameters, if you assume that at a given choice of parameters, what is the equilibrium state? Right? Then this is just e to the power minus eta p of x. So in general, I just call it Hamiltonian of x lambda by rate of lambda. Right, so this is one choice where I just take the I mean to be the equilibrium state at whatever lambda is at the instantaneous lambda. Okay, and then this immediately can be identified with the free energy of the system at that lambda, the equilibrium free energy. Because, so free energy at this okay, so if I use this choice, then it leads to
Can you just try it? Okay, so.
So these systems, okay, where you have the time dependent parameter lambda,
Right.
then you make it constant and you get this canonical. Right? Yeah, that you wrote.
In this case I wouldn't do this.
No, that's
Right,
not
yeah, in
my-
this
my-
case I wouldn't. So this is systems where, let's say you just have one temperature, right, which is this beta.
Yeah, so this is
Right, yeah. In this kind of sense, I'll come to that. Right, I will do it.
Obviously,
Yeah.
so, I don't able to understand that entropy produced over a single trajectory. Entropy should be the number of V or number of the concept.
Yeah, that is the usual equilibrium entropy. But now we want to define entropy during like a process happening.
Is what that physical means? What that physical means? Physically, how we can.
I mean, you see, it's okay. Right now, maybe it's not clear what is it physically. Okay, so sometimes I, like for various choices of this thing, you can identify this omega like as the work done. Okay, so physically it's just the work done on the system, or the work done minus the free energy change. So I mean, depending on your choice of this, it gives choice to various physical quantities. Okay, but the main idea is that it gives you a notion of irreversibility. Right, I mean, the fact that the forward trajectories are more probable than reverse. So the other thing is, independent of the choice of Pn and P0, what you can also, I also showed, is that you can ask what's the probability of entropy produced in the forward trajectory because omega divided is equal to e to the power omega times e minus of. Okay, so this is what is the probability that in time t, if I average over all possible trajectories, then what is the probability that I will generate omega entropy? Okay. So this is different from this statement, and here I still include forward and reverse paths. Okay. So now we'll see that. So this is again very general. It's valid for any choice of Pn and P naught. Okay, so now for with this choice, what I showed is that you can derive things like, I won't write them again, you can derive Jarzynski, Hooke's fluctuation theorem, and also the fluctuation theorem proved in Hooke-Chan. Okay, so in Hooke-Chan's case, there's no lambda dependence. It's just a non-conservative force driving the system. And in Jarzynski's case, it's typically there's no non-conservative force. There's just a lambda dependent parameter. Okay, so so all this follows, and then other choices that you can make are.
I have a question.
Yeah.
Since if the system is not in equilibrium, why are we interested in the probability distribution at equilibrium?
Probability distribution, this one?
Yes.
No, so initially I could, like in this experiment, so initially it could be in equilibrium, and then I'm doing something. Okay, and right, yeah, that's the idea. And I mean, for example, this Jarzynski's equality, which gives you e to the power minus. So if you use all this, what you get is okay. So you take, let's say, example is like you take a polymer, okay, and so one of the interesting questions is what is the free energy of a polymer as a function of the distance, end-to-end distance, let's say. Okay, so in this experiment, what you do is you take a polymer and you pull it to some distance, and you repeat this large number of times. Okay, so you start from equilibrium. At initial time, it should be in equilibrium, and then you just pull it. Okay, if you do it large number of times, you get different work each time. You do an average over all these configurations, you will find that the change is exactly at the initial endpoints. There's a 20 equilibrium free energy, right? It just depends on the length of the polymer. So it gives you this equilibrium quantity. So it's kind of relating some non-equilibrium process to an equilibrium result. Okay, so and it's just something nice that comes out from this formalism, right? And it's obviously very non-trivial results. Yeah.
For the experiment you just described, the end point of the process doesn't have to be in equilibrium?
No, yeah, that's the important point. So you take polymer, you have a bead or something, and so there's some distance L, right? And you just pull it from, so let's say initially you hold it like that, and then you pull it to some distance in some finite time tau, t. Okay, so you pull it from x naught to, okay, maybe this right notation, 0 to RT. Okay, so now initially it's in equilibrium. Now when you pull it, of course it I mean, if you ask what is the probability distribution of the polymer's configuration, you have to solve the Fokker-Planck equation, right? So at the end, I mean, of course you will get some, you start from equilibrium distribution, so P of this entire polymer configuration at t equal to 0, it was in equilibrium. Okay, now you solve this Fokker-Planck, you will get P of x at time t. But if it's a finite time and you are doing this process, obviously it won't be in equilibrium at this time. Right? But still this result is true. Okay. So and the free energy at this state is a well-defined concept, right? Which is what you are using here. But you don't care whether actually the polymer is in equilibrium at the end of this process. That's clear, right?
In the beginning,
in the beginning it has to be in equilibrium. That is important.
I mean, but why? I mean, for example, if in the beginning it was in equilibrium, I pull it infinitesimally.
Yeah, if you do a quasi-static process, it will be in equilibrium all the time.
No,
and
what I am saying that the nearby point, as soon as I will pull it, it will go out of it.
Yeah.
So I am saying that if I go very close to that initial point, So, I mean, there will be, I can also define free energy over there, right?
Yeah.
For example. So, free energy difference is there, and free energy, a third point, which is the final point.
Yeah.
So that, what I'm saying, I'm trying to say that, can I extend this to this case where in the initial point is also not in equilibrium?
Yeah, then you have to, okay, if the initial state is not in equilibrium, you'll get something different. You won't get this. But you have to work it out. You'll get something. You won't get, because initial free energy is, you won't get this relation.
Just related,
Yeah.
something I asked yesterday also. Then in that case, using Pn from the Boltzmann distribution, is it a mathematical trick?
Yeah, you can, you can think it's a mathematical trick, but it gives something useful. That's the point.
Because we know that P0 should be from equilibrium,
Right,
it is
yeah.
clear.
Yeah.
But Pn also, why is it chosen like that? Because it
No,
seems to be
yeah.
crucial to the
To get these
derivation.
relations, but it's you can use other definitions. It's still useful.
But since we're talking about delta F,
Yeah.
final state also has to be equilibrium.
No, it's I'm saying in your experiment it need not be in equilibrium. Of course, you can if you wait at that stage, it will eventually equilibrium.
So the
You
way
will
you do
equilibrium.
experiment is you put it,
Yeah.
wait for 1 hour and then repeat the experiment like
No, you don't have to wait for 1 hour.
I mean, I just made that up, but you have to equilibrate the system so that you can compute F at the final point.
No, so this I'm saying, supposing you're interested in finding this, okay. So then, of course, this protocol automatically gives you delta F, change in free energy. Okay, you don't care whether at the end you're in equilibrium. Of course, now you wait till you reach equilibrium and then this free energy makes sense at that point. But I'm saying you don't have to wait. Of course, you have to, initially when you start, you have to make sure it's in equilibrium and then you pull it.
But then how will we get delta? So delta F is
Delta
over
F
the
is-
cycle.
Delta F is this is a well-defined change in equilibrium free energy.
So this is from, I'm just not understanding delta F. So you
No, this is
start
something you want to find. What is when you pull a polymer at this configuration and this configuration. What is something you are interested in finding a change in free energy of this polymer. Okay. Then I am saying you can do this non-equilibrium process, where you start from the initial things in equilibrium, you pull it, and then you do another experiment again. The initial is at the end you don't care what it is. Okay. But by doing this average, you automatically find delta F.
delta F is between R0 and R2.
Yeah, the equilibrium free energy between this configuration and this configuration.
Can I say something? I think one way to see is this, let's say you want to compute the left hand side, e raised to minus beta W average, starting with an initial condition which is equilibrium. You do that computation, and what you will get is that on the right hand side, you just simply get partition function of the final by partition function of the initial.
Right.
So it's just a mathematically that partition function of the final turns out to be corresponds to an equilibrium distribution of the final position which is R. And then you identify that as a free energy, so it gives you a way to compute the free energy.
But when you said partition function, so we are assuming that it's some kind of...
No, you don't have to assume that the state is equilibrium at the end. You're just getting it as a mathematical
Yeah,
trick.
just think of it as a very mathematical. Yeah.
So, is this assuming that the final state is just characterized by RT? Say I had another macroscopic variable.
Yeah,
Say
no.
it was the same flexible polymer.
Yeah.
Which has some bending rigidity. So RT is not the only macroscopic.
No, so even for a semi-flexible polymer, see whatever it is, there's a microscopic model for the polymer. It
There
is
is some
flexible,
microscopic.
semi-flexible, all sorts of interactions. But finally, I might be interested in I'm characterizing the polymer by some macroscopic variables, right? Which might be just the end-to-end distance.
Of which end-to-end distance might be 1, is what I'm saying.
It's one of the parameters,
It's
right?
one
Yeah,
of the
there can be other
parameters.
parameters also, right? Yeah. Like temperature, of course, is a
So
parameter.
what I'm saying is that this end state, this RT,
Yeah.
that does not specify, that's not a
No,
complete
not the
specification of the
concentration.
macroscopic.
Right, yeah, that's why initially I was writing X, then I wrote R, because it's not the microscopic, it's the parameter, lambda really. So this I should really think of the parameter in my, that I am controlling.
No, I thought we are talking macroscopic variable, right?
No, so this end-to-end distance of the polymer, right? Like this I can manipulate by putting like some bead and pulling it, right? So this is what I can control. So this is like my lambda of t, which I can externally control. Internal degrees are all inside, like x1, x2, the polymer positions and all. Yeah, you can control it in many ways. I mean, you could put an electric field here and change it with time.
The actual position of the bead, the state of the bead and the initial electric field.
No, I mean, see, in the experiment, this is what they do. They attach a bead here, and actually, like you can put it in a trap and you drag it. Like at least small polymer, this is how they do the experiment.
I mean, if in the experiment when they drag it,
Yeah.
and so in the same they will take it back, right?
Yeah, you have to take
So
it.
when they will take
No, it
it
means you
back,
just release it and then you will go back, you have to wait for some time, it will reach equilibrium.
so it has to be waiting periods, has to be.
Yeah, it has to be. So that's why it may not be the most efficient way eventually. Right, yeah.
But one of the things that is E minus doesn't need to be the reverse process. And this is an important insight thing in the field. That this is an auxiliary process where you can put whatever you want.
Yeah, reverse process, you don't need it.
If you put one process, you will get entropy production. If you put another one, you will get work. So you could do an experiment where you do both forward and backward, and you're interested in the statistics of forward. Still, in B minus, you can put something that is not the backward process.
Right, yeah.
So there is some freedom, and I'm sure.
Where is the scale of the system into it? Whether it's microscopic, mesoscopic, or macroscopic, in all this formalism?
See, in principle, this is valid for any system, but then the fluctuations will become, like to make it observable, you have to have small systems. Okay, now small, of course, it's I mean, you have to typically these experiments are done with polymers, which are maybe even I think I don't know 100 base, like DNA molecule with maybe 100 or 500 base pairs. Small ones, right? Because otherwise, from the average and fluctuations, it's difficult to make out. Yeah,
Can you say what the microscopic degrees of freedom are and what are not
No. Yeah, microscopic degrees of freedom in the polymer are the monomer positions. Right? So you have like n monomers and n1 expression, and this is I'm fixing the endpoint. I'm controlling that. That's like lambda of t. And all this polymers, the monomers on the polymers are the microscopic degrees of freedom. Yeah. Okay. Yeah.
Can we not say the non-equilibrium quantities are different from equilibrium quantities, just like in linear response theory?
Say again.
Left-hand side will sort of.
Yeah. Okay. Yeah, you are asking whether it's related to similar to linear response. Yeah.
So,
Actually, yeah.
The question is that see, linear response theory is valid for small perturbation.
Right.
So validity here is
Yeah. That's. I mean, you can think of it kind of even. So linear response is small perturbations. This is like beyond linear response. And actually, from some of this, you can derive linear response, Green formulas, and so on. Okay.
So in this formalism, so R0 is the center of the trap, and X is like the end-to-end distance.
No, okay. So forget the X1. So see, polymer means like you have lots of particles. Right. So let's say this is R1 bar, R2 bar. So I mean, so this is like my X is now consists of X. So X is now set of all these variables. So all these are this n monomers forming my chain. This is my stochastic variable. It's like 3n dimensional space, let's say. So I have some, but now I can control this polymer by some external parameter, which might be I hold the end polymer in a trap, and I can move this trap. So that is like my lambda of t. So this, so the center of the trap is really lambda of t. So position of trap. Okay, any other questions?
So system goes from equilibrium state to some other state. So the rate how the system goes is also important.
Yeah, I mean, if you can either move it slowly or you can move it fast. It's, I mean, it will have different entropy production and so on.
Okay, so it is incorporated in the entropy.
Right, yeah.
Sir, if the system goes from equilibrium state to a non-equilibrium state, like what will the free energy then be?
No, see, that's what I'm saying. Like, free energy is defined when it is in equilibrium. So finally, when you are computing free energy, it is for the polymer which is at R0 and a polymer at RT in equilibrium. That is well defined. When you are doing this protocol, you don't care what happens at the end. It may not be in equilibrium, but you can still compute if it was in equilibrium, what was the change in free energy. Okay. Yeah, I'll continue. Okay, so like I was saying, this relation is completely general, but from that you can now derive various other things. And so one immediate consequence of this is also very general, which is that e to the power minus omega expectation is equal to 1. Right? Okay, so yeah, so this is one choice of T0Pn. The other choice is like you could just assume that Pn okay, so you could actually assume that it's the solution of the Fokker-Planck equation. So you could start P0 in any distribution, any initial distribution, and then look at P at the time at the end point. Let's say it's just the solution of the Fokker-Planck or master equation. Okay.
So by any, it can be.
It will not be in equilibrium. It could just start with anything. Like Ye did, right? He started with some squeeze state and you can look at. So and then you just look at the solution of the Fokker-Planck. Okay. So this if you do again, of course this results are valid, and then you can prove some other things. Okay, so some of these actually different choices of P, and including this choice, is discussed in this report. I think it's reports in, it's a review, so you can find it in physics reports or reviews in progress in
Progress.
okay, but it's a review.
Some review.
Okay, so this has
Progress physics. Okay.
progress in yes.
For sure.
Okay, but it's a long review, and it has most of what I discussed. It also discusses these different choices and so on. Okay, so this is one choice, but at least I mean, you can't get out much, I think, from this choice. So the other choice that also is kind of useful is take P0 x as P steady state, and also Pn. Okay, so these are the different choices. So what does this mean? So so this is for processes where. Okay, so let's assume there's no time-dependent parameter, and you can drive the system to a non-equilibrium steady state either by a non-conservative force or by boundary drive. Right? Those are the two ways you can still drive the system to non-equilibrium steady state. So now you choose your initial condition P0, and also this final distribution, just the P steady state distribution. Okay. So in this case, one nice thing that immediately follows is that the forward and reverse processes are both the same, right? Because there is no lambda t. So forward and reverse process are both the same process, and
We should have reports progress physics.
okay, I have started right. Reports in progress.
Progress physics.
Someone says strange name.
on progressive position side.
Okay, so so let's discuss this choice now. So in this choice, what's really nice is that forward and reverse are the same. So you can write E of omega by E of minus omega, both for the forward process is equal to e to the power omega. Okay, so this is, I think, okay, I don't know who's, okay, so this was, I think, first discussed in Leboeuf's one, which pretty much they write this relation. Okay, so now from, this is, yeah.
Forward and reverse are same, does it mean both the processes are equally likely?
No, both the processes are they're the same process. If I reverse, like in earlier, if I had lambda, then the reverse process is a different. See, if the forward, like supposing I vary lambda versus time, in the forward process, it goes like that, right? But in the reverse process, I said it starts from here, so it looks like I'm like that, right? So it's a different process. But if there's no lambda, then forward and it's the same thing. Right, so that's the idea. Okay. So now, what can you? Okay. So a few things that you can also get from this is again something that Arnaud mentioned yesterday. So typically, so there's this distribution of the entropy produced, and then you can ask. So quite often you're interested in the form of this distribution, and that's one of the interesting questions. What does this distribution look like? And one other quantity that people quite often define is something called a generating function for this distribution. This is just T of W.
So lambda W minus lambda omega, sorry.
Minus lambda W omega. Right, yeah. Okay, so now what we can see is that we can get a. So let's say we have this relation, which is some form of a fluctuation theorem.
Sorry, Abhishek,
Yeah.
so this process doesn't, this has a lambda. This doesn't have a lambda, right?
This doesn't have lambda, no lambda, right? I switched off no lambda.
No, but this lambda is different.
Oh, sorry.
You
You can put this.
Yeah.
Yes, in entropy.
That's fine.
So that is lambda T. The subscript is there. This is lambda direct.
Okay, yeah, let's use lambda. But I think it cause confusion. Maybe. Okay, I'll use lambda actually because it's the standard thing that.
You pick lambda is lambda.
Okay, so now supposing I multiply this by e to the minus lambda. So this I can now change omega to minus omega, so then this becomes d of omega. So this means, so implies so this is, so this is the same information as this, right? So the z of lambda contains the same information as p of omega, and this is the statement of fluctuation theorem in terms of the generating function. Okay, so this again, see this is, so omega is the entropy produced in a time t, and so it's valid for any time small or big. Then there is this other set of theorems where actually one is looking at not omega, but instead of omega you look at the entropy. Okay, so supposing you are just interested in knowing the properties of this quantity. Okay, so instead of omega, which is this plus this change in system entropy, if you are interested in just knowing does it follow any kind of fluctuation theorem, then it turns out that what you can show is that, okay, so first of all, like I said, the entropy, if you are doing a let's say the simplest example you can think of is you have some chain connected to different temperatures, right? So the entropy generated is clearly delta beta times the heat transferred from hot to cold, right? This is the usual thing we know. Now this, of course, like if you wait for long, it's increasing with time, right? So typically in a non-equilibrium process, entropy generated grows with time. Yeah.
When you change this omega to minus omega to omega,
yeah,
your limits are also going like plus into.
No, but
minus omega. Your limits there, but what about we need some property of P omega?
Omega is
just
minus
yeah, let's change it.
Also, since
but that go ahead.
Since you have the generating function,
Yeah.
directly calculating expression of omega, one can do that, right? Directly.
Do what?
Directly calculating the moments for omega or.
No, you can do what? Yes.
I mean, since you have the generating function.
Right, yeah. From the generating function, you can calculate all moments. That's what, right, yeah.
So, is that useful, like, to see if you want to compute like expectation of u or omega?
Right, yeah, of course. Yeah, so that is, it's the genetic, if you take log of that, that generates all equivalents of omega, right? So that's
So maybe like the average of omega is, say, this total entropy of that means that,
right, yeah.
That is an important part.
Well,
What about the higher moments? Like, are there some physical?
Oh, right, okay. Oh, yeah, so this is something I'm not discussing, but like from these fluctuation theorems, you can relate like the, if you do these expansions, what you can show is that, for example, delta beta is related to, let's say, average Q.
Right.
Okay, which gives, and the relation is exactly the Green-Kubo formula. Okay, so it will give you a linear response. If you look at the higher moments, they will kind of give you some higher generalization of fluctuation, linear response here.
No, because in standard stochastic process we always look at like the different like moments and like currents
Right,
and
yeah.
things like that.
Yeah.
How would one relate those things here to the thermodynamics?
Right, yeah. So the first moment, of course, it's easier, but higher moments, direct physical, like connection to thermodynamics, I'm not sure, maybe it's bigger, like the higher moments of this object, how is it related to thermodynamic quantities? Yeah, I don't know if there's a simple, but you can use this to actually derive equivalent of linear response theory, but at a higher order. So nonlinear response theory you can kind of derive.
No, but does it, for instance, also for this particular process, does it make some connection about the nature of the moments? Like, for instance, this JC.
Oh, because of this relation?
Yes.
Okay, that's your question. Right, okay.
Because it may give.
Right, yeah. No, yeah, so that's what I'm saying. Using this relation, you can generally use proof, for example, if you do just a first order expansion, you can derive exactly Green-Kubo formula. Not this one, but the other version that I'm talking about. The steady state fluctuation theorem. This one I'm not sure, but the steady state fluctuation theorem will give you usual linear response theorem. Okay, so if you look at omega instead of omega, if you look at just this part of the entropy produced, then you do not have this exact equality. Okay, so there what you can show is instead that okay, so first of all, P of SB. So like I said, SB scales with time, and what you can show is that this distribution P of SB has typically form which is like exponential of T into some function of, okay. So typically it has this structure, and this is called a large deviation function. So this is called a large deviation form, and this is a large deviation function valid only at large times. Okay. And then what you can show is that in this large time limit, this H satisfies a similarly, if you define Z of lambda, so Z of lambda has the property that it goes as e to the power t some function of mu of lambda, and mu lambda again has this property that mu of lambda is equal to mu of.
So, this P of SB that P is very large, this form is e to the power t is very large. Is this kind of universal, like irrespective of the non-equilibrium process?
Right, yeah, it's almost always true that it scales. I mean, because you can see it should scale with time, right? If you wait longer, there's a non-equilibrium process going on, more time, more entropy should be generated. So, and this is the average rate of entropy production.
So, this SB by T, that is independent of, is that there is no explicit time dependence? Means once I calculate, say, SB.
Yeah. So SB by T is the average. Of course, this is a fluctuating variable, right? In different but so the average is what I'm looking at, and that also is has some distribution, and then this satisfies this property.
This T, so this T multiplied by H, right?
Yeah.
So, so is it a kind of like homogeneous functions like T?
Which one? This one? No. See, T is the prefactor. And then H is you can think of it, this is the scaling form of this SP. So SP, P of, this is a function of SP and time, right? But now I'm saying this will have this particular scaling form, where it comes as exponential of T into some large deviation. Like this is the, it is always SB by T.
Rate. Kind of rate.
Right, yeah. Rate of entropy production. Right.
So this linearity that is being
what
linearity time that is always a problem. It cannot be linear problem.
No, it's okay. There are like people have looked at some not in some time not exactly in this kind of processes I'm discussing, but like if you think of like Levy walks or something, you can come up with large deviation where you might have a different exponent, but not for usual.
It's T is per minus T times that, or have you changed something?
Where?
In this definition.
You're saying minus? No, what are you saying?
T is per minus T times the large deviation.
This, I mean, you can write minus of course. I mean, I can put it in H. But, right here.
H minus H minus H.
Oh, sorry.
So, in this situation, you have to consider that there is no external force.
There's no.
So this
This no. You can have a non-conservative force. That is okay.
Even in this situation.
Right. Yeah.
But how do you ensure that? Okay.
Yeah. That is still. You shouldn't have a time dependent.
No, so this is for specifically this situation. This P of omega is equal to for this, or it is more general.
No. See, all this is true for omega, and this is valid for any time. It can be small, large, anything. Now I'm saying if instead of omega, you just look at this part of the entropy production. So there is entropy. Omega had these two contributions, right? Beta delta Q and then the change in system entropy, that log of P naught minus log of Pn. So if I forget that part, if I just look at this part, then this is, then for just this part, this is no longer valid exactly at all times. But what is valid is kind of the same relation but at large times only.
Steady state
Fluctuation theorem, right? Yeah. This is what is like. I think Spohn-Lebo is discussed it, and first it was Gallagher-Cohen in for Hamiltonian, not Hamiltonian, dynamical systems.
So is it only for the path that SB, or it is also true for any function that scales with time, like for example work or something?
Yeah. So I mean, finally it's this function that is. But even for work, you can try to establish.
So that's also
right. Yeah. But you may not always get. If you can identify it with entropy production, then you can. But in general, this is the entropy production, right? In terms of forward by reverse trajectories, and this is what you can show satisfies this. Okay, so this proof is very easy in some sense, right? Because it's almost an identity. You just do something. This is more non-trivial, and I think if you look at Spohn-Lebo, it's kind of.
The proof means from there to the t tends to infinity limits.
Right. Yeah. So you don't start this way, but you have to use different. See, naively, you might think, okay, this is omega was SB plus this log of minus log of P final plus log P initial. So this of course grows linearly with time, but these are bounded functions. Okay, if you let's say you have a system which is, its energy can't grow and it doesn't diverge. So then these properties are bounded functions, and then these can't scale with time. Okay. So therefore, at large times you might think, okay, that you can just forget this and it should still work. But it's it's kind of non-trivial.
So this is in Spawn.
Spohn-Lebo has this proof of idea for both jump processes and Langevin processes and yeah. Huh?
The reference.
Spohn-Lebo is GSP 1999. Yeah. P naught equal to Pn equals to P steady state.
So in that case, what is the difference between omega and SB?
No, because see, this is P final and P initial, so it depends on. So this is at x, evaluated at the final point. Right? So this is there's still x n. I mean, it's the same distribution, but the end, where it's evaluated is different. Right? This is evaluated at x naught. So that's why it's different.
So perhaps a naive question. So why do we like Legendre transform it? Speak in terms of lambda.
Oh, this no. So okay. I mean,
is there
like,
any advantage? Like,
no. So usually generating functions you introduce because they are sometimes if you want to really compute this distribution, it's easier to do it in z of lambda. That's the main reason. And also, yeah, because like Amitava said, if you expand this, if you take log of this and you expand it, it gives you all the moments of the omega.
but because experimentally we just compute omega directly.
Right. Yeah.
So then we
Yeah.
have to go to lambda.
No. Yeah. Experimentally, probably this is the either you do this.
Like
Right. Yeah. Or you do the yeah, last time whatever form. In omega, that's the easiest thing.
In all the theory papers, they all have this lambda, which is
But
but
it's the same thing. This and this has exactly the same content. This
Yeah.
and this have exactly the same content.
So how is, I mean, I understand lambda and omega are related to each other, but how exact, I mean, I understand the equations, but
Yeah.
like how do you think about it?
No, I mean,
It has the inverse dimension of omega.
Okay,
Basically,
No, I mean,
that's true.
see, if you just like expand this, it gives you all the moments of.
yeah.
like
It's the moment generating function.
Yeah, Taylor expansion is the Taylor expansion of it. All the coefficients you will get moment.
Yeah, I don't think any experimentalist will plot this quantity. So I don't know. I don't know. Okay, so I think I'm done.
No, what you are saying with HS minus SB by T, I mean, you are negative means
No, see, okay.
large deviation function. It's just a property.
See, I'm just writing this P of omega and okay, so in this case, what I said is that if you replace omega by delta, so let's say we are interested in this distribution. So this is it's almost the same statement as this, but this is true at large times. Now I just put in that form. P is e to the power t times h of okay, then I just take log and I get basically that. Yeah.
So this, as we're talking about this largization, so the thing is that we have to go to this very large time, and then we will see that the probability distribution will fall into that.
Yeah.
So do you have any, like, can you give any idea, like, for example, I'm simulating single particle in alpha dynamics on two particles.
Yeah.
Then how long I should go to
That,
in simulation? Catch
yeah, that will depend on parameters and whatever you're using. But what you should see is look for convergence, right? I mean, do this and if you do at short times, it won't have that scaling form.
Yeah,
So this is scaling, usually scaling, like when you get a scaling form, you have to just increase time and see when it collapses. Like you do data at different times, right? And then try this, if the data collapses, then you are sure that
like
it's
a finite size effect that we could do, and
right,
similar.
Yeah, it's finite time, you will get some finite time corrections, but at large times you will collapse into
This Z lambda, that mu should have a mu lambda t.
No, here it doesn't have. So this, I mean, okay. See, because Z of lambda.
Because you have a lambda omega.
Right, yeah. So, so Z of lambda is equal to what is d of, let's say d of omega. So let's say small s, where small s is p by t. This is what I wrote, right?
Because it is omega
Oh, sorry, D that is. This is fine, right?
Yeah, but then the H, you are writing SB by T as.
Yeah. So this SB by T I'm writing as.
Then it's not a problem.
Right. Now, okay, sorry, this is, maybe I should write this as, because originally defined it in terms of capital S, right? So now I should write T into
That is what I was saying.
small s. Okay. So now you can see that this is equal to D of S. Okay, and now if you want to do this integral, okay, so you can just do, let's say, saddle point, right? Large case. So if you do saddle point, you get lambda plus h prime s star equals to whatever 0. And then you solve for whatever and you put it here. Right? So if you do that, you will find that this will be just a function of lambda. There's no t now. So this is just, yeah, it's just follows from saddle point.
No, I mean, if you have removed this constant part over there, right? Because SB was, you are saying scaling as t, and it is very large in comparison. But if I keep that thing and I lead to, so it leads to finally a constant term over there, right?
No, yeah, but it is because it's a fluctuating variable, you can just put some constant. And sometimes it has large scales and it messes up. So, I mean, it looks like you can just
SB
forget.
by t will be a finite term. Right?
Yeah, it looks like a finite time which shouldn't matter.
Oh,
but it is kind of
qualified.
So here we are not putting any assumption on the distribution PSP, whether it's a Gaussian or
No,
not.
anything is fine, right?
So as long as we can define a large division.
Right, yeah.
But is there a theorem or something that always defined, or are there some distributions where you not define a large division? Because
I mean,
we have seen like sometimes you just don't converge to a single function.
I mean, at least it depends on, of course, yeah, it won't always have, but depends on the process you're looking at. So at least kind of the processes I am talking about, it should have. I would expect it should always have a application.
For example, yesterday we saw like very non-Gaussian entropy.
Yeah, but that is fine. Non-Gaussian is no problem. It should still satisfy exactly the.
So,
yeah,
like this unrelated question, because this results at the steady state is more relevant for like most of the non-equilibrium systems we study.
Yeah.
So, and I mean usually like other than stochastic harmonics, people look at transport properties and like correlation. So you are saying about this Green-Kubo gradient.
Yeah.
So if suppose one knows these transport properties, so then one can directly relate to like what will be in terms of energetic. Are there known like already worked out results?
No, you're asking if I know something like, for example, linear response relation or whatever.
Yes,
can I use
yes,
it to get some information about this? You see, this has no, it's because I mean, from here to this is much beyond linear response, right? So just if you have linear response, you can say a bit about.
We can
this.
go from here to there.
Right. Yeah. Right. Yeah. So this you can think of like a generalization of linear response, beyond linear response.
One very stupid question. I thought that omega was alternate relation for S total.
S total. But S total was S bath plus.
Correct. SB plus.
Yeah.
So how did that SB by T come into picture, because T was?
No, T is just okay. See what is okay. This is yeah. So SB was the total entropy produced in a time T, right? Then I'm just defining. So I can. Then what I said was SB scales with time.
Yes.
Okay. So now, therefore, I'm interested in the average entropies. Let's say. Okay, so then I just. So So this is the average entropy.
Production rate.
I see. So now you are, but rather, okay. So you are just saying that I define omega to be SB.
Right. Yeah, exactly. Not omega, but S. So I can't put here SB first of all, right? Because there's no exact fluctuation theory relation. But the equivalent form is something like this. Okay. So instead of omega, I'm basically putting S because it's just a simple 1/t transformation. Right? So if something is valid for omega, it should also be valid for omega by t.
Yes.
That's.
It's because like at last times it's just the path entropy which plays important role.
Right. Yeah.
Because
Yeah,
system
yeah.
is minuscule.
Yeah, system is minuscule plus it's bounded entropy.
And
The change is bounded.
then effectively you're talking about production rate rather
Right,
than
yeah.
the
Right, yeah. Because otherwise it's a growing thing, right? But I just want the rate of. Okay. Okay, I think that is okay. So now I'll go to this time, right?
Yes,
We started 9:30.
we started little bit.
Right. Yeah. Okay, so now it's very general discussions, sort of philosophical discussions. Okay, but before I start, I'll just make one point. Since this is a school on biology, one of the motivations is biology. So then one question is, can you apply this to active matter, right? And there it's kind of tricky, okay, because active matter are systems which don't satisfy detailed balance. Okay, so then how do you do this, right? So it becomes tricky. And yeah, so I was recently in some conference where there was a talk where, like, so the main idea is how do you define forward and reverse trajectories, for example. Okay, so yeah, so in I was in this conference where people discussed, let's say, typically if your active particles, they kind of carry an arrow sometimes, and there's a center of mass and there's the orientation vector, right? And maybe a forward trajectory might be it goes like that. So the center of mass moves and the arrow also does something. It follows the arrow. So now if you think of time reversed trajectories, so see time reversed trajectories, I mean usually the way I've defined it, they are also physical trajectories, right? They make sense. Like in the under-damped case, velocity is reversed, so it's exactly what you observe in a movie if you reverse a movie, right? And the reverse microscopic level, the reverse movie also makes sense, right? Okay, but now if you reverse these guys, I mean, it doesn't make sense, right? So this guy always makes sense, but if you reverse, then obviously it doesn't make much sense. But you can, of course, talk about this. You can define all this stuff, but in some sense, it doesn't make sense. So in this talk, what I heard is that there was another definition of the reverse trajectory where you just flip these arrows. Okay, so you not only look at the reverse in position space, but you look at like it's like velocity flipping. Okay, so it's like you look at a trajectory which looks like that.
I don't get it. Why flipping doesn't make sense? Sorry, I'm very dumb.
Yeah, it's like you might think it's like velocity flipping.
No, like if I get a trajectory like this. I mean, because
If you reverse time.
Yeah, but it's a reverse trajectory. You won't see, like if you think of a movie, you won't see the arrows flipping, right? Okay, I mean, no, because there's no, let's say you have particles like this, right? Like the kind of particles you study.
Yeah, they can go backwards.
They can go backwards, but if you reverse the movie, you don't see that, right? You see something very strange.
So the arrow represents the internal coordinate of the particle,
right, yeah.
not the velocity.
Right, exactly. Yeah. So that's why there is some, so in this talk there were like people use various definitions and you can get various notions of entropy.
But there could be some trajectories where there is no internal coordinate. For example, just position of some Brownian particle.
Yeah.
And you reverse back its position, just reverses back. So there is no internal variable. If there is no internal variable, then does it still not make sense?
No, but like example, like if all this ADP, UP, I mean, no, I'm saying active part. Yeah. So in active matter, usually like ADP or RTP or whatever, there's always some internal arrow, right?
So the prescription is you switch the arrows.
No, I mean you have various prescriptions. So at least in this talk, what I heard, okay, I don't know much. Okay, I'm just saying what I heard is they use various possible definitions of reverse trajectory. Actually, there were 3 definitions. I forget the third. and you can define all this entropy produced because you need this forward reverse trajectory, right?
But this is like a passive system.
Yeah.
So here we are talking about some active particle is there and there is a directionality. So to get the reverse trajectory, you not only have to flip the this thing and you also shift the direction as well.
Right. Yeah.
Right. So this is also true for magnetic system, right? For taking the particle there and then for getting the reverse trajectory,
you have to flip the magnetic field,
right?
right? Yeah.
As well.
Right. Yeah. You have to flip the magnetic field.
So here also is another variable that you have to flip and you just get in the direction.
Right. Yeah. But it's yeah. I mean.
But all the differences in magnetic field is all over. Here it is a local.
Right. Yeah. But yeah. So I mean, somehow this is a bit unphysical. I mean. Okay. So anyway, and what I just wanted to mention is that there are many choices of how you define reverse trajectories, and they lead to different into production and so on. So I mean, there were a few talks in that conference, and there was always a lot of confusion. Okay, so I don't want to get into that. But yeah.
So, but this confusion arises only for polar particles. If you have an active nematic, for example, then
okay. Maybe it's better, right? Yeah, that
then
is,
the normal formalism will follow.
maybe okay. So yeah, I don't know.
Not at
Yeah,
single
right.
particle level, but at
Right, yeah. So this I don't know.
I mean, with nematic or apolar particle, at single particle level, probably there is no confusion. But once you go to larger, like collection of particles, then you can't play backwards.
Yeah. So anyway, this I
cooler or pusher kind of objects.
right. But yeah, so this was just to motivate like what I'll talk about later. I mean, in the now using the slides. Okay, so I don't want to
Because of the intrinsic polarity of the particles, the nematic.
It's only intrinsic polarity, or I mean, it's active particle when you are saying, so it will be taking something from environment and doing it.
Yeah, they also have their own dissipation at internal.
That is a local thing.
Yeah, so I mean, ideally, what you should do is, I think there's a paper by Seifert who there's a long paper by Seifert where he discusses entropy production in active systems. And I think what he does is incorporate internal mechanism which is giving rise to this directed thing, which satisfies detailed balance. So if you look at inside, then again, finally it satisfies it. And then you can refine everything, and then take the limit where you trace out this degree of freedom. Right? So that's when we want to wait. Okay, so right here. So now I'll go to this models of cyclic heat engines. Okay, so like I said, this is very qualitative discussion, and I mean just some thoughts on basically things called autonomous heat engines. Oh, so this is some old stuff that so this is, I just want to say that this is a book by Pera, Brownian Movement and Molecular Reality, which I strongly encourage people to read because I mean basically if you read like the beginning of this book, you'll see that he was already in some sense thinking of stochastic thermodynamics and violations of second law, like transient violations of second law and so on. So it's some quotes from his book. Yeah, so he even talks of on this like perpetual motion that you see when you look at Brownian motion. Okay, so now I'll talk of autonomous engines. Okay, so basically the question that I want to think about is, I mean quite often when you see these microscopic engines, like you have to, like quite often you see that there is some protocol which involves like maybe moving or squeezing a trap as a function of time, which you need a laser to do that, and so you have to do a lot of things you have to externally do, control, right? And then you kind of run an engine. So engine basically means like in some like you have some you have some cycle. So this you can do by like various examples are there where you at the microscopic level, if you want to do what an engine does. You have to manipulate the system, but you have to do it by there's always external control. So now question is, so by autonomous I mean that it runs on its own. Okay, so you don't have to, because that looks very complicated, right? You have to use lasers and all that and do various things, and then you get a little bit of work out. I mean, it's not what you want to finally. Okay, so I'll talk of some examples of this Stirling engine. So I think there are a number of papers which discuss this, but I'll discuss a couple of papers. So one is this paper that I write from 2016, which discusses a mechanical autonomous stochastic engine. So so what the engine is basically, it looks like this. So basically it consists of, there is one. Okay, so basically it's this object here. It has 3 degrees of freedom, this system. So it has, so what you can see is there is a cantilever here, and then there is a kind of a ribbon between this fixed, so there is this fixed thing which has, and there is a ribbon which can vibrate. Okay. And then on the top there is another ribbon which can push the cantilever, and so the cantilever is where you can extract work. Okay. So there is basically this system has 3 degrees of freedom, and this guy is connected to a, so it's red, it's the hot path, and the upper ribbon is connected to a cold path. And then what the authors claim is that this is all you need. Okay, so you can write some equations of motion which I have written for this system with 3 degrees of freedom. So xh is the hot ribbon at the bottom, and xm is the upper ribbon, and xw is the cantilever. So so for this you can see it's a standard Langevin equation, right? So there is a noise and dissipation, and then there is some nonlinear interactions. So so it's just a standard set of equations, and what they show is that this can, I mean, so you just have this hot and cold path, and it keeps running, and it has a cycle like this. Okay, so this is the cantilever displacement and tension, which, and the area under this will give you the work done.
So is it like utilizing the expansion and contraction of ribbon?
Right, yeah, so those, the motion of the ribbon is basically like the contraction and...
so that means that the other set of engines where the trap is externally within,
yeah.
Here it is not required because the ribbon itself, when you put it in the hot, it expands, and then in the cold it contracts.
Yeah, it's always in contact. So it's not like you have to put it in contact.
Okay,
it's always everything is always in contact.
So there are 2 ribbons.
2 ribbons, yeah.
One is in hot and one is in cold.
Right, yeah.
Can you give a reference for this?
This is one ribbon, this is the other ribbon. This is the hot ribbon, this is the cold ribbon. And that's a cantilever. The reference is this 2016. Okay, so this is not an experiment, this is just a theory paper. So they wrote those equations and did simulations, and this is what they got. Ribbons are decoupled, but there is interaction. So in the equations of motion, you can see that there is interaction between all of them. So you can see dissipation, BH, XH dot, and there's a noise, Z of H.
You say one of the ribbon is coupled to hot, another is purely to the cold.
Right, yeah. So that is the hot ribbon, first line.
Okay.
That's hot path, right?
Okay.
Then the second equation has a cold path. And the cantilever, you can just think of it as like there's an environment, so there's still some noise.
So how is it different from any Carnot, Stirling, or any engine?
Carnot engine, okay, it's very idealistic, right? But Stirling engine, okay, yeah, Stirling engine, it's they are trying to model a Stirling engine, which at a microscopic level. Right? Now, normally, if you think of Stirling engine as a microscopic engine, you don't care about fluctuations and all. But now you want to do it at a microscopic level, and this is what they are proposing.
So, I mean, from where microscopics are entering into this?
No, because otherwise you wouldn't care about noise.
No, I mean, these variables are
Because they are small
noise.
objects, so you can, so you have to write all the noise terms. Okay, so I mean, yeah, so actually this, if you look at the paper, I mean, like one of the problems here is, it's not clear, like you have to work with extremely high temperatures and all, like, I think it's like million, yeah.
So, what is the ribbon is pushing? Is it a rod or a ribbon?
The ribbon. It's a, but you can finally, it's just the, I mean, you can just think of this amplitude of this degree of freedom, which is driving the cantilever. Right? So finally, you just write some simple coupling between the cantilever, ribbon, and this guy. Okay. So what is, if you, okay, now I'll come to real engines, where it's actually very important to have inertia. So I'll come to the real engine now. Because, okay, so because, yeah, so let's see how a real engine works. Okay, so I'll show this really beautiful engine where we, does if you, is this video not? If I don't do play mode, it plays. But if I do, but now it can show. So it doesn't show. If I don't do play mode. Yes, share screen. Okay, so this is a Stirling, simplest Stirling engine, okay, which actually you can buy on Amazon. It's a tiny thing, and yeah, and you can see how easily it works. Okay, so you just take some hot water and you put this thing, and it immediately starts running. So, I mean, it's, this is what one would like to make, right? But maybe at a microscopic level. Okay, so, yeah, so this is really a very, very amazing device, which So this is a long video, you can watch it. Okay, so you can see basically it just has these two cranks, and then there's this there's a piston out here which is going up and down, and then inside there is yeah, so that's a metal surface. There's the inside. There's a so this is the cold surface. The bottom is the hot surface, and inside there's some there's a kind of piston which is which can allow air to pass through. Okay, so it goes up and down, and it so this is what drives that thing, and but it can also allow air to go in between the two parts of that chamber. Okay, so now let's look at this thing a bit more closely. Okay, so this is what it looks like, and you can see it more slowly and exactly what's happening. Right? So now, can we write an equation of motion for this system? Okay? Because eventually we want to write we want to take it down to very small scales and write an stochastic, like what is the effect of fluctuations. But first one would like to write a sort of equations for this macroscopic device. So yeah, so what are the variables that you need to?
Yeah. I mean, there you have an air movement, right? That air is going out.
Yeah. So here inside there's air, so it can't go out. Okay. So its air is trapped inside. It can go between these two sides, through the sides of this piston. Okay, and then this is the sort of main work piston. This one, it can be like, you can make it zero weight, it doesn't matter, okay? And it need not have any thickness, but it should just allow air to go in between these two chambers. Okay, so now so this system, if you think of like what are the degrees of freedom of this system, right? What is the simplest description of this system? So this was analyzed in this paper, nonlinear dynamics analysis of low temperature differential kinematic Stirling engine. So this is 2018. Right? So this paper is still looking at the macroscopic engine. Okay, not looking at small scales, but just at the macroscopic engine.
Last number 5004.
5004. Okay, so now okay, so this engine has again a typical engine has this four kind of cycles, and okay, so actually it's described by just one variable. Okay, so what you need is maybe in the next figure it's clear. Okay, so this is, so there was a student at ICTS who was working with me on this project, trying to understand this dynamics of the piston. So he has drawn this very nice picture which tells you exactly what's going on. Okay, so this is the lower surface where you put it on this coffee cup or whatever, and the upper plate is cold, okay, and sides are all insulating. And then in between there's this piston which can go up and down, and there's kind of hot air and cold air. But I mean, what we'll see is that it's okay to assume that this inside air is at a single temperature. Okay, and then there are these two sort of shafts which connect to that object. So what you need is in typical engines like this is that there's part of the process where this gas is driving the whatever load or whatever there is. But part of it has to be, inertia has to carry it around. Okay, so inertia is really important in this kind of systems. Okay, so I mean, so you see these two rods going up, and they are connected. There is a phase difference of pi by 2 at the points at which they are connected. So it's rigidly fixed at those 2 points, and there is a phase difference of pi by 2. So that is important. And as a result of this phase difference, okay, so now this angle theta that you see out there, So there is this angle theta, which is the angle of some fixed axis with the vertical. Okay, that's this rotating thing. So that is the only degree of freedom in some sense in this system. Okay. So we want to write an equation of motion basically for that theta. So what are the forces on that theta? That's what we want to write. And how does this exchange come about? Like how does it affect all the dynamics? Okay, so this is, let's try to write an equation of motion for this system. Any questions?
How is it really working? That what is going up and increasing the pressure in that upper chamber?
Pressure is increasing, that pushes it, and then okay, and then see, it will push and then it rotates. But at some point, all this cold air comes through, okay, and then there's no longer enough push, but the inertia just carries it.
But don't you need a pressure, a higher pressure on the blue side?
No, yeah. So you don't get that higher pressure, but the inertia just pushes. I mean, makes the wheel go, and because of that, it goes down.
But how does the wheel start to move?
So initially, if you don't do anything, it will just stay like that. Okay, you have to give a slight kick. Okay. In the movie, maybe there's a small perturbation will do it. But if you look at the dynamics, one of the fixed points is nothing happens.
So the first thing, the cycle has two halves. First half is there is the expansion that pushes up,
right?
And then there is inertia that probably comes down. That is the second half of the cycle.
Yeah. So these are the how the cycle works. Okay. So initially you can see that it's there. I mean, and then the piston is in some position. As it goes up, that thing goes like that. But then it drives it. It's because of inertia. It just goes down. Okay, and then
but the thing which is very difficult to understand is how the temperature of the air is changing. It is fast because first it is hot down, it pushes it back.
Yeah.
Now again, how the cold air gets cold and it get compressed again.
Yeah. No, it's not easy.
That
I mean, and if you. Yeah, it's quite amazing that people could think about this, right? And make such a device which works. I mean,
no, but
think about it, it's hard.
How, I mean, this mechanism I am not able to understand. I mean, when it expands.
Yeah, when it expands, then because the pressure is building up here, it will then air will go down, right? So this is cold air is coming and getting in here, and again then it absorbs here air and it pushes the piston. Okay. So this keeps happening. I mean, but when it pushes, I mean, then of course, because it's happening at a faster time scale, things are not yet, they'll slowly go. Okay, so.
What is the relevance of this pi by 2? Why it has to be pi by 2?
I mean, anything other than like pi, anything, if it's pi, it won't work because it's completely symmetric. Pi by 2 kind of breaks the symmetry. Right, like otherwise there's nothing breaking the symmetry. Like you can ask what fixes the direction of motion. Right? If you make it 3 pi by 2, it will go the other way.
The other way.
Right, yeah. So, but pi it will nothing with that. Okay, so yeah, so these are the equations of motion for this system. So the first equation is kind of easy to see, right? So I'm just writing an equation of motion for this guy. So this is the, what is it called, this thing?
This.
Huh?
What is
Flywheel, yeah, flywheel, okay. So flywheel, and this will, if you take some fixed axis, and this is the angle theta. Okay. And what I showed is that it's attached here. So this is rigidly fixed here, and another point pi by 2. Okay. Now, so I'm just writing an equation for this wheel. Okay. So that's I is the moment of inertia around this here. So I double theta double dot equals to the force from. So basically, there's a torque from these guys. So that is that F sine theta. Okay. And then there's just friction. Okay. Now F sine theta, where does that come from? So that is so the force on that. So the force on that is so it's basically the force on this piston, and that is sorry on this piston, the red one. So there's another piston. Okay, so the force on this is the air pressure minus the pressure of the air. the pressure inside minus the air pressure outside. So that gives the, so basically pressure into area is the force. And so you can see that's what, so if you look at the second equation, force is, the force that appears in this equation is just the difference of pressure. Okay, and the pressure inside, the simplest assumption you can make is an ideal gas, and it's just kT by volume of this chamber. Okay. Now this volume, because everything is related to theta, right? So whatever volume you have, the inside this thing is depends exactly on theta, right? So you can calculate the volume in terms of just theta. So the position of the theta completely defines the volume of the gas. So yeah, so you can if you compute it, so V of theta is just given by in terms of the area of the lower chamber and the upper chamber and some. So this is some small calculations. Okay, so this is one chapter, and then what we need is also how does the temperature change, because the temperature inside is changing constantly. So the simplest assumption that in this paper they make is it's the temperature is constant inside, but it's changing with time. Okay, and then you just use the second law, the first law, energy conservation, to write the change in energy. So the change in energy, this specified into dt, is equal to the heat absorbed minus the work done, right? So that's
this capital gamma is a friction.
That is the standard field.
That is the
that wheel thing, right? Yeah. And yeah, and you can, if you really want to get work done, you can also apply a load right there. That would put additional force. Right, yeah. But otherwise, it's just friction of this. Right?
So the hot air is going from below to up in a finite time, right?
Right.
How is it homogeneous?
Yeah. So that is the assumption. It's not completely clear, but that's what they assume, that is just a homogeneous temperature. Okay, and so from this equation you can immediately write the rate at which the temperature is changing, and now the only thing you need is what is the rate of heat input, right? And for that what they assume is that it just depends on the temperature. So there's some, so this is the temperature inside of the gas, this is the of the cold bath, which is at the temperature at the top, and this is the temperature at the bottom of the air. So there's heat going in and going out, and it's just the difference. So you just assume some linear model. Okay, so then you get these two equations which I put it in blocks. So if you use this and this in here, you get this equation. So it's two set of so it's actually there are three variables, right? Theta, theta dot, and temperature. So these are the three dynamical variables, and you have some dynamical system, which is so this is some nonlinear dynamical system. Okay, so now you can what they do is you just solve this equation, and you find that it has a solution which corresponds to this exactly what you observe in the experiment. So it goes round, and you can extract work.
It's a nonlinear limit cycle.
It's a nonlinear limit cycle, right? Yeah, it goes into. So there are various. At least I saw that. I mean, if nothing happens, is also a fixed point of the dynamics, and then there is this limit cycle which keeps going. Okay, so yeah, so this, I mean, I have seen some other papers which like have done some molecular dynamic simulations of the same model.
So this is from that EPL.
EPL paper, right? Yeah. So after that, I've seen a more sort of microscopic modeling of the same model, where you pretty much like put in molecules out here and then try to look at it at a microscopic level. So yeah, so there's one paper on that, but there's no so far paper which studies it at a level of stochastic thermodynamics, and so that I think is a sort of interesting question, open problem. Maybe someone is interested. Okay, so there's one other recent paper that I saw which also discusses this particular system, and also some other model of autonomous engine. But this I won't discuss. Okay, so I think I probably have finished time. Okay, so maybe I'll stop here, and Yeah, so if there are questions, and so I won't be able to. Discuss entropy. If in the discussion session there's some time, I will discuss the last point.
So, yeah, about this engine, like at stochastic level, are you assuming that we'll get rid of the moment of inertia?
No. At the stochastic level, I just want to add, supposing I bring it down, right, then fluctuations become important.
But the inertia is still there.
Inertia is still important. Okay. So this paper that I showed, they also, so one of the things they say is that you can actually also make engines without having inertia. Okay, because what they say is that in at least biological systems, typically inertia seems not important. Right? So then how do they work? So one of the things they also discuss is how to get rid of inertia but still do autonomous engines.
So actually this the basic design is the non-linearity, right? Somehow some
non-linearity
is there, and that actually helps that
right.
We don't need to like
do anything, right? You just let it, that should be ideal.
And that is due to
some instability and it goes to yeah. So now it's very interesting question, what does fluctuation do to that?
So it is cyclic.
So all traditional like big macroscopic engines, inertia is definitely important. But now question is at a microscopic level, is it still crucial? Okay. So this paper, this PNS paper 2022 that I mentioned, there they also discuss some engines where you can, even without inertia, you can kind of build autonomous engines.
So this fixed point solution, a stable fixed point, for example, for fluctuations, will it give you the
it's a limit cycle which is probably stable. I think it's stable. Yeah, it should be stable.
Fluctuations can drive down to the fixed point and probably not.
Probably not, right? Yeah, but that's an interesting question.
But the equations that we showed is almost, except noise, all the it's not much difference if we down the scale, right? Like unless
so you just have to be okay.
We have this D2I, just can we just go to the equation? So this equation, so this is the underdamped inertia term.
Right, yeah.
Then there is some potential, say, sign.
Yeah.
Then there is a damping.
Yeah, so there I mean you could just add
the
noise.
Saying that you can.
It satisfies fluctuation, right? Yeah. But at the inside, I mean, of course, like all these are fluctuating now, right? DQ and there you have to be, you have to know how to do it.
So energetics is the
right. Yeah. So I'm not modeling heat baths, right? Because heat bath I would also model by Lazarus equation.
yes.
Here I'm just saying average rate.
Put the noise there.
Right.
Then
Yeah.
I have to
Yeah. So right. Yeah.
I wish it's a live question, but you differentiate between motors and engines.
Motors and